Welcome to the Random Interaction Seminar Series of the Department of Theoretical Physics at TIFR Mumbai. Today we have with us a very old friend, Arun Paramekanti from University of Toronto. Arun actually started his career way back in TIFR. He did his PhD from TIFR. It's a very long time back. He then went to Santa Barbara, then he went to Berkeley, and then he has been in University of Toronto for a while now. So today, Arun will talk to us about multipolar orders in d-orbital materials. So over to you, Arun. Yeah.
Hey, thanks, Rajdeep, for this invitation to participate in this thing, and it's so yeah, I've had long connection with TIFR, and it's been a while since I visited, but hopefully once this COVID is a little bit calmed down, hopefully I'll get a chance to come see everyone there. So what I'll talk about today is some work that we've been doing over the past year or so, related to what's called multipolar orders, and I'll kind of talk about sort of this work in the context of a specific materials. And I don't know how it works with questions, but just feel free to stop and ask questions at any point, or if you type it into the chat. I'm not sure if I'll be able to view it, but maybe Rajdeep can interrupt.
I will keep track of the chat.
Yeah. So if there's anything I miss, just feel free to interrupt. And yeah. Right. So this is work actually goes back to thinking about magnetism in in its various forms. And in fact, the very simplest form that we are all familiar with is ferromagnetism, which of course has very clearly manifest macroscopic manifestation with like your refrigerator magnets. But we already know from dealing with condensed matter systems over the last 50, 60 years that that already, if one goes to the next simplest level where the dipole moment of the electrons orders in some more complicated fashion with moments that have spatial dependence on the scale of the lattice constant, already it's kind of hard to imagine that such things exist in a crystal, unless one resorts to kind of more sophisticated probes like neutron diffraction, where the neutron can come in and its dipole moment and the momentum transfer of the neutron are such that you can actually start visualizing orders of this sort, which are modulated on the lattice scale, right, of few angstroms. So what multipolar orders refers to is the idea that one can have even more complex forms of magnetism, not just associated with the ordering of the dipole moment of the electron, but also associated with other more higher order multipolar operators that can emerge in certain cases, right? And in particular, it's been well known in the context of a lot of these heavy fermion systems, so things like uranium and neptunium, which some of these actinide elements that if when spin-orbit coupling is very strong, so I've kind of abbreviated here with SOC here, then it can actually drive states of local states of the system, which involve both spin and orbital degrees of freedom that are kind of mixed together. So it's kind of roughly indicated here by the shape of these wave functions. Basically tell you something about the orbital that the electron lives in, and the color kind of indicates its spin content. Right? And in fact, there's a very interesting old News and Views article, of course, based on research that was done even earlier. But there's an interesting News and Views article that kind of emphasizes that the difficulty of trying to probe and detect such what people call hidden orders. In other words, even though it might be visible in thermodynamics, for example, things like specific heat might show that there is a phase transition occurring in the system. It's very hard to directly detect these kinds of orders, which is what kind of leads to this terminology. And so Vikram has been has done a lot of work on these kind of things in the heavy fermion compounds like uranium, ruthenium to silicon 2 in the past. So in fact, one of the simplest examples of this, one can sort of very quickly illustrate with thinking about spin model. So going beyond the spin half of the electron, if you imagine sort of two electrons that somehow are locked into a spin 1 state at a given site on a lattice, then one can imagine Hamiltonians, which are more general than the simple Heisenberg S dot S, which involve sort of bilinear squares of S dot S, which is allowed for spin 1 operators. And already, if for a Hamiltonian that's parameterized in this fashion, where you have some component with Heisenberg and some component with this so-called biquadratic interaction, the phase diagram is quite rich, and among other phases like this Haldane, this singlet Haldane phase, or dimerized phases which break translational symmetry, there are two regimes here where one discovers that there are what are called quadripolar power law quadripolar phases which exhibit some kind of nematic correlations. And this was proposed a while ago by Andrei Chubukov, many years ago, and there has been a lot of numerical kind of DMRG and other studies. Many people have worked on this kind of Hamiltonians, realizing this kind of quadripolar correlations in this spin 1 system. And in fact, it's quite straightforward to kind of ask, where this comes from in system like a spin 1 magnet, is to realize that, okay, once I go from a spin half to a spin 1 system, one has local operators that one can define, or if you want to think of local order parameters that you can think of, there are basically on a site you have with 3x3 matrices for a spin 1 problem. You have 9 Hermitian operators, which include, aside from the identity and the usual dipole operators, there are these quadrupole operators which involve sort of products of the spins, like things like Sx times Sy, Sy times Sx, which are a set of 5 quadrupole operators that one can define for the spin 1 problem. And so in fact, it's precisely these quadrupole operators, or and the terminology then comes from thinking of classical analogs of things like liquid crystals. You can think of quadrupolar order or nematic order associated with these kinds of spin 1 magnets. And so that's what I was referring to here in the phase diagram, that because one is in 1 dimension, these only have power law order, but in higher dimensions, one can have a true long range order at 0 temperature of this kind of quadrupolar operators. So what, whoops. Right. So what I wanted to focus on today is to ask, whether one can discover sort of experimental versions of these higher spin systems and normal orders. So where would one look and in a certain sense, I'll kind of discuss this. Where would one look, and how do you detect this, right? So those are the two main questions. And if you think about this, with you clearly, if you want higher spin systems starting with an electron, you want to think about local systems where you have many electrons at a site, right? So you want some many electron Hilbert space at a site where you can construct these higher spin degrees of freedom, and then you start sort of coupling them and asking what kind of orders you can establish. So what we know from here already is that one way you're going to get higher spin is that at the microscopic scale you have some kind of Hund's coupling between the electronic spins that can give rise to a large spin angular momentum. In general, if the system has orbital angular momentum, you can also get a large orbital angular momentum because of the Hund's rule. And the spin-orbit coupling will couple them. And you can sort of think of this, either spin-orbit coupling is larger or smaller than the Hund's coupling, and that will depend on kind of details. But these are the places where you can imagine that this combination of Hund's coupling and spin-orbit can give rise to a number of interesting higher spin degrees of freedom. Right. So this, as I mentioned, has been most well studied in the context of the heavy fermion systems, where spin-orbit coupling and interactions between electrons are quite large. They're all on the scale of 1 to 2 electron volts. Hund's coupling, okay, I don't know like a very proper estimate, but it's all comparable. These are all on the scale of electron volt scales, right? And what this leads to is the formation of well-defined levels with total angular momentum on an atom or an ion, right? And so you form, large L, large S, and you couple them together to get some total J angular momentum states. And then these electrons, which are highly kind of localized, start sensing that at the next level, they start sensing the crystal field splittings because it's not an isolated ion in free space, but sitting in the solid. And so what one does is then kind of rewrite this crystal field physics in terms of these angular momentum levels and kind of figure out what the structure of the low energy degrees of freedom is. The things I'll focus on today are 5D systems, where the underlying microscopics is somewhat different in the sense that the Hubbard interaction is still quite large. It's on the scale of electron volts. The crystal field splittings are also large, right? And so these lead to kind of what you might think of as well-defined orbital degrees of freedom coming from this physics here of crystal fields and Hubbard interactions. And then the spin-orbit coupling and Hund's coupling, all of these are kind of subdominant on the scale of these things up here. Right? And so the hierarchy is somewhat different, but we'll argue that the physics is kind of similar. And so in fact, the physics of multipolar orders and so on, which have been more extensively discussed in the heavy fermions, a lot of them will also play a role in some of these heavy d-orbital systems. Yeah. And because this is TIFR, I should point out 5D is not 5 dimensions, but yeah. So okay, right. So these multipolar orders, in fact, I mean, this is not something which it's actually something where people have thought about this, how to probe these experimentally. And in fact, a couple of places and where people have looked for this is using optics. And in fact, there is two papers that, not two papers, a bunch of papers, but on two different classes of systems, one of which involves a square lattice, a kind of a layered lattice of these iridium ions, a layered square lattice where you kind of dope it, and people have argued that the magnetism that's present in the system basically disappears. But when you go above this magnetic phase transition in the system, which is associated with dipole nail order, there is some kind of hidden order phase transition which people have detected using second harmonic generation. Although there is some debate on exactly, I mean, again, so this is experiments from David Shear's group at Caltech doing nonlinear optics, but there is some not very clear idea of what this transition is. They had some proposal, but I think they're kind of revisiting exactly what this phase is supposed to be. But they detect some sign of a transition, which through optics here. A somewhat more, possibly clearer example, comes from these pyrochlore systems, cadmium to rhenium 207, which is it's a metallic system. It's not an insulating magnet. It's a metallic system, and it had been proposed that you can have a kind of unusual form of quadripolar order. So if you recall, the quadripolar order that I had defined earlier was made entirely out of spin operators. So it was Sx times Sy plus Sy times Sx, for instance. But in an itinerant system with mobile electrons, one can also imagine making this out of electronic degrees of freedom, where you tie the momentum of the electron and the spin to construct combinations which transform in almost the same way. So it's kx times sy plus ky times sx. So under things like rotations and so on, they would transform similarly. But this actually transforms differently under inversion. So whereas the quadruple operator formed purely out of spins is even under inversion, this particular one would be odd under inversion. And so there has been this thing to look for this kind of parity breaking quadrupolar orders. And again, if you break inversion, there is a clear signature in things like second harmonic generation, which is only allowed if inversion is broken in the system. So there has been, again, some work using optics to try and nail down the form of this kind of quadrupolar order, which would be associated with some deformation of the Fermi surface and some accompanying spin texture on the Fermi surface coming from the locking of momentum and spin degrees of freedom. So what I wanted to focus on is more on some of these insulating systems rather than the metallic example that I was just referring to. And in that case, in fact, it's helpful to think in terms of a very local picture, like I was mentioning earlier. And so this, in some sense, is a hierarchy of, typically what one has. You start with atomic d-orbitals, right? And there's a very large crystal field splitting. So if you're in an octahedral crystal field, OH, then the electrons basically split into single particle levels, which are these T2G states, which is a threefold, excluding spin, it's 3 levels. And then you have an EG doublet that's sitting up here with about 3 to 4 electron volts above in energy. Right? And this triplet here basically transforms, you start with an angular momentum 2 for the electron in this d orbital. But once you split this with crystal fields, it transforms like an effective angular momentum 1 degree of freedom. Okay? And when you turn on spin orbit, then the single particle levels are of the form where you have a spin 3/2 quartet, total sort of angular momentum 3/2 quartet for this electron, split from an angular momentum 1/2 and coming from this coupling of L equal to 1 and a spin half. And in fact, the most well-studied examples of this kind of crystal field physics has been in systems where you have 5 electrons in this T2G, right? So you kind of fill up all the 4 states down here, and you partially fill this J-half system here. And this has led to kind of interesting physics associated with Mott insulators, where you imagine that this set of 4 electrons, you can forget about them. They're all filled states. And you have a half-filled level here, where if you now turn on hopping, these electrons can hop around and either form metallic bands, or if the repulsion is strong enough, they can lead to insulators with some very unusual forms of magnetism. And there's been a huge amount of work on this, and people like Shubro and so on have worked a lot on this in the D5 systems. Okay. So what I wanted to turn to is to ask, well, how do you know that this hierarchy is there? And one way people look at this is to actually measure this crystal field levels that I was referring to. So I was kind of talking about these set of levels here. But you can actually see them by using 2-photon measurements. So you come in with light, like X-ray photons, and you can excite from some very low energy states here, let's say some 2p level or somewhere, into one of these states. So let's say you excite to an available state here, which might be in an EG state. and you de-excite from a T2G level. And so the photon in, photon out, you basically end up getting some energy that is transferred to the system, which corresponds to this excitation gap here, right? And so in fact, you can sort of do this as a function of energy transfer, and you see basically these peaks, and these peaks can be associated with various transitions between these crystal field levels, right? So this is, on scales which are, like 4, 5, 6 electron volts energy scales. But in fact, you can start looking at this at energy scales which are also associated not with the T2G to EG, but also with these spin orbit levels, right? And so in this case, you can have electrons which have various occupancies, right? So you can have just one electron. So the one I talked about earlier was when you had 5 electrons in the system, but you can of course explore this physics at a variety of electronic fillings. And people have worked a lot on this, in the context. I kind of briefly mention a little bit of this. And some of the work that I'll kind of talk about today are at a certain filling where one finds this unusual type of multipolar. Right. So how do you, see this? So now you can sort of start doing the same spectroscopy, but now at lower temperatures. So this is really like doing the like an atomic physics type problem, except now you're doing it with the these spin orbit levels of an atom in the solid, right? And what one finds is that so the bottom here are experiments on a bunch of compounds. So these are rhenium, which is like with 2 electrons. This is an osmium compound with 3 electrons. This is another one. This is an iridium compound which has 4 electrons. So you can sort of do this at various fillings. And now we are exploring energies which are below that 3 to 4 eV. So you're looking at kind of the lower energy scales in the problem. And you see that again, instead of a single level, which would correspond to, exciting across this gap, you would have said, well, what can I do? I can come here from a core level and I can de-excite from here, but that involves no energy transfer. So you would have thought that should be like an elastic kind of thing. Or you can sort of excite into this level here, this doublet here, and de-excite from one of these, right? So for all these fillings, you would have thought that there should be a single peak which corresponds to this energy difference between the J3 half and the J1 half. And clearly that's not true. Because once you put in interactions, of course, this level is not just 2 electrons here will actually split the degeneracy associated with how you put these electrons into these 4 levels. And in fact, it leads to kind of a structure of an excitation spectrum, much like for electrons in an atom, right? And one can do a very simple, toy model where you just take this spin and orbital angular momentum and add interactions, and you can very easily basically see that you can reproduce the kind of spectra for this resonant inelastic X-ray scattering experiments, which are kind of where I've compared calculations that I've done with these RIX experiments, and one can sort of reproduce these structures reasonably well. With parameters which are kind of similar across these different systems. So it's about, like 0.35, 0.4 EV for the spin orbit coupling and somewhat smaller for the Hund's coupling. And with that, you can sort of reproduce all these things. So that's one way you can see that what I was saying earlier is kind of, in fact, the right and reasonable picture for these things at the atomic level.
So Arun,
Yeah.
This is essentially just atomic orbitals plus Hubbard U type calculation with maybe few orbitals, or is it?
Yeah, so this keeps basically so this is looking at energy levels which are below the T2G EG splitting. And so this is keeping the 3 T2G orbitals, keep the spin, and keep the Hubbard interaction.
I see. Okay.
And this is not, this is just a single site calculation there. Right. So it's like diagonalizing some, I don't know, like some 100 by 100 matrix is the largest probably that you will ever need. For maybe even smaller actually. There's only T2G. So it's like 20 by 20 matrix or something. right? And you can sort of see that you get the, so the only thing here is the energy levels are easier, but you can also see that if you use this this Kramer's Heisenberg kind of formula for this, you basically even reproduce things like the intensities and in fact, they have used just X-ray diffraction measurements and magnetic X-ray diffraction measurements to look for this quadrupolar order. Okay? And so quadrupolar order, because it's time reversal invariant, right? It's kind of in systems with inversion symmetry, quadrupolar order basically is tied directly to time reversal invariant charge order in some sense, or orbital order really. And so here one finds that you get something where you have a coexistence of electrons that want to live in this kind of x square minus y square and 3z square minus r square orbital. So there is some kind of combination of these orbital ordering in the system, right? Together with magnetic order that sets in at a lower temperature but points along certain directions. So it's not collinear magnetism, but it's magnetism where the dipole moments point along two different directions on the different sides. And so this again, at higher temperature you see this, and at a lower temperature they find this, at least qualitatively similar to this picture. It differs in some details. It's kind of quite different.
Hi, Arun. I have a question. Can I ask?
Yeah.
So the idea is that this quadrupolar orders sets in and they affect the exchange coupling of the spin-spin interactions, and finally whatever the exchange coupling does, it dictates the nature of the spin order, lower temperature spin order. Is that?
Yeah, it should be, because the orbital order happens at a fairly high temperature compared to the spin order. So the exchange interactions are probably going to be quite different in the symmetric phase versus the quadrupolar ordered state.
And a related question then is that once the quadrupolar order sets in at around the temperature, it sets in. Does one see strong phonon signatures also?
No, so this is something we are working on at the moment. So in terms of the excitation spectrum, it turns out there are somewhat subtle signatures in the low energy phonon modes, but not, so it's not like there is a clear soft phonon, for instance, that you see where there is some mode. So you would think that, this should be like a cubic to tetragonal transition, for instance, right? But the signatures are quite weak and subtle in the low energy phonon modes that we've been looking at together with Bruce Garland.
And why is that? Do you understand why that is so?
Not
Because
very clear.
generically, one would expect strong phonon signatures, given that it's like this Piles type of argument that there is an order parameter which is time reversal invariant, so it linearly couples to the lattice degrees of freedom.
Yeah, so this is exactly why we got into this, which was that the expectation was that here is some static signature of this order, right? But you would have expected even precursors of this order to show up at even higher temperatures, or things like soft mode, and then you should be able to see this physics. Now, it's not very clear to me why this is not very strong, but one possible thing that the coupling might be weak is it might be like a numerical thing, which is that that the T2G orbitals are not kind of pointing towards the oxygen. So maybe if I think of some kind of even like a Jahn-Teller or something where deriving orbital order you think would be a good thing, it's possible that the energy change is not dramatic.
I see.
As opposed to a lot of the EG orbital based systems, for example, like in the manganites, where it's like a much more dramatic effect.
I see. That's interesting, because one would expect that to be true for f-electron compounds, but you're saying that the energy scale can also be low for d-electron compounds.
Right. So for d electrons, so this is the claim that I've heard, right? So the thing is, I think spin orbit coupling partly alleviates the problem that I think you tend to prefer, somewhat more symmetric things, but you do get, you do expect, even, imagine I just had one electron in a J3 and I forgot about, details of exchange interactions for a second. You would have thought, well, this should be just Jahn-Teller unstable, right? And the Jahn-Teller instability, for instance, could drive a distortion of the crystal. So this could just be some kind of cooperative Jahn-Teller distortion in the system. But in fact, the impact on the lattice seems to be very small. In other words, the lattice, when they do these diffraction experiments, they can see the extent of the distortion, and it's an extremely small distortion. Unlike many of the 3D compounds with EG orbitals, where this is a very strong signature, here it seems to be much weaker.
I see. Thanks.
And it's possible that, if one looks at the higher energy phonon modes, maybe, the signature and some of how this impacts some of these phonon modes might be more clear. Here, what we find from looking at the analysis of the, phonon modes that my student and I, we've been looking at, what happens to, what are the types of low energy modes that get affected. So people have measured phonons in the range of, like up to about 70 millivolts. And a lot of the phonon modes are not directly related to this EG order. So the phonon modes typically at low energies are things like rotations and so on, right? And so you do expect that maybe the signature on those modes is probably more subtle, because it will be that, if you have some combined, x square minus y square and z square, you probably end up tilting your orbital in certain directions, and maybe you will expect some more subtle things in the tilts and rotations, because they couple only at second order to the quadrupoles, couple only at higher order to those kinds of tilts and rotations in the system. But maybe we can come back to this later, maybe if you have more questions, Shubham.
Yeah, sure. Thanks.
There is one question which is asking, apart from RIXS, what other experiments would be sufficient proof of existence of orbital ordering?
Orbital ordering, so orbital ordering, you don't need inelastic X-ray, right? So this is just X-ray diffraction to look for the orbital order. But if you're talking about the levels, structure of levels, excitations in the spectrum, in the excitation spectrum that I was showing, then people can even do like high energy neutron scattering. So you can come in with, if these splittings are on the scale of even like 100 millivolts, or, you can come in with high energy neutrons and actually see excitations between these different orbitals, which people have done. So that's another possible probe. I mean, optics for sure, right? But I don't know any use, optics that's been done on this, and I think that's a useful experimental thing to do in the future, is to look for optical signatures of some of this physics.
So Raman is not at all useful for this?
No. So all of those. So when I said optical, I meant both, linear as well as 2-photon Raman. So the Raman in some cases, so I will argue that in fact Raman is useful for the octopolar order that I'll talk about. But in some of these cases, if you're looking at modulated orders, then it's harder to do with Raman, because that's looking at a zero momentum transfer. It's looking at kind of uniform orders, as opposed to staggered orders of this sort, where there is some layer to layer, there is a difference in the orbital order. That's harder to get than with Raman alone.
Yeah. Okay. Yeah.
Mm-hmm. Right. So what I wanted to focus on then in the talk is look at systems where instead of one electron, which was kind of the focus of what I was talking about earlier, is to kind of ask what changes if we look at other fillings, and in particular, looking at just the 2-electron sector of this exact same problem. Right? And there's a large class of these compounds containing osmium, and there are other examples. There's just one set of examples that the experimentalists were working with that we were talking to. And these nominally would realize J equal to 2 spin moments. Okay. And there were some puzzles in the data, kind of very similar to this kind of idea of hidden order that was there, that I mentioned in the uranium, ruthenium 2 silicon 2 problem. Although that's kind of a much more celebrated example. Here, there are some similarities in the sense that, okay, you see something in a specific heat when you cool down the system, then you go to about 50 Kelvin and you see evidence of a single phase transition. This is some impurity stuff happening at low temperature. There's evidence of a single phase transition at about 50 Kelvin. Yeah. And so this is different from the D1 example where there were 2 transitions which were clearly seen in specific heat. Here, it looks like there's 1 transition in the system at which you want to kill your kill your moments that are kind of free here will all get ordered at a single transition. But if we look at the entropy, so if you sort of integrate up the specific heat divided by temperature across this transition out to, let's say, twice Tc, right? One finds that the entropy that you recover is actually quite small. It's more on the scale of about 5 to 6 joule per mole Kelvin when you go through this transition out to 2 Tc, which is more like a doublet rather than having log 5, which would be like 12 or something. In units of joule per mole Kelvin, it would be like 12 joule per mole Kelvin, and here it's kind of half or less. And so to compare, it's not even of this order here, right? So log 3 already would have been like 9. It's quite close to log 2, the entropy change. So somehow this picture that you have a J equal to 2 with 5 states, which should have given you log 5, is somehow incorrect for this system. Right. So one way to kind of do this is to say, well, maybe I start with 5 levels for the J equal to 2 moment, and somehow there is a phase transition at high temperature, well beyond all of these scales that you're seeing here. Maybe at 300 Kelvin, 400 Kelvin, there's a transition where, let's say, part of that entropy gets quenched, right? And then when you come down to 50 Kelvin, all that needs to order is this second phase transition, which is leading to the killing of that doublet into a unique ground state. Right? But in fact, there is, so one scenario would be that, even in the system, there are 2 transitions. The higher temperature transition you're just not seeing, and the lower temperature transition is the one that you're seeing. So that's one possible explanation, but we'll argue that that's not the case here. Or not necessarily the case. You don't need that second the upper transition is not necessary. Okay. This one actually comes to, not quite to, partly to Shubhro's question, which is that, if, for instance, that there was a higher transition, right, where something analogous to this quadripolar ordering was happening in the system, then you would have expected to see some change in the structure. Okay? Admittedly, these are very weak in examples where we know them, they are actually quite weak. And so one has to do fairly high resolution X-ray diffraction experiments. And these are, the data in black dots here are the X-ray diffraction kind of, focusing, zooming in on one peak and kind of scanning through it. And what is shown as these solid lines are simulated data, assuming a distortion in this case, which is about 0.1%. Right? And already you see that this Bragg peak with a 0.1% distortion should have been visibly split, but in fact, it shows no sign of splitting as a function of temperature in the system. Nothing changes. Yeah. And so clearly, anything that's happening in the system is probably nothing to do with any changes in structure. The structure stays cubic as you cool down to the lowest temperature. But below this 50 Kelvin transition, people do see signatures of oscillations in the muon spin relaxation in the system. So you implant, so So for those who are not familiar with this, so you implant a muon in the system, which then decays, and the decay product tells you, has information about time reversal breaking in the system. So your muon basically sits in the magnetic fields. Imagine there are internal magnetic fields in the system. The muon precesses in that local magnetic field where around the site where it is sitting, and then basically it decays and it emits positrons, which you can then go and sort of measure and kind of see, get some information about this time reversal breaking. And as a function of time, because this muon is precessing your signal from, if you look sort of what you call sort of forward versus backward, you see that there will be some oscillations which signify breaking of time reversal symmetry, right? And this is seen, it's, if you're at high temperatures, then this is all kind of random fluctuations, and you end up basically just getting a decay of the signal. But when you go below this transition at about 50, maybe 45 Kelvin here, you begin to see well-defined oscillations, about 4 or 5 periods of oscillation. And so that signal here, the muon signal that you see here, this oscillatory signal basically tracks something like an order parameter in the system. Okay. So the first thought that the experimentalists had when they did these experiments way back, about 5-6 years ago was, we have detected dipole order, because if the system has dipole order, it would have time reversal symmetry breaking. And so this phase transition at 50 Kelvin is associated with the electron dipole moment. Okay. But in fact, that cannot be the case, or at least it's not, it cannot be the case. If we look at the strength of this internal field, right, it's on the scale of 50, 60 gauss, and it turns out to be an extremely small moment. Okay, it's on the scale of about like a 20th of a Bohr magneton. Okay, whereas the J equal to 2 magnetic moment that you would have thought of is actually quite sizable. It's on the scale of like 1 Bohr magneton, right? Whereas this is at least a factor of 20 smaller. The kind of fields that you're getting here already telling you that there is something odd about it, right? So either it has to be close to some critical point, some kind of quantum phase transition where you're going from some non-magnetic state into a state that has very weak magnetic order, or it has got nothing to do with the electronic dipole moment at all, and it's something completely different. Yeah, but somehow I don't think that was quite clearly recognized in this older work, that this is actually an unusually weak field, and that something that is an important question. So in more recent work and things that we were sort of collaborating, the experimentalists, they actually went and did a very careful neutron diffraction study to look for what is the size of this moment. And the only thing they were able to do is basically place bounds on this. So like I was saying, it's kind of consistent with the mu-SR experiments, but they've now explicitly gone and checked, and they find that they see no detectable moment, and the best thing they've done is just place bounds on this detection, right? So the best bound here is on the scale of like a 20th of a Bohr magneton. Okay. So this is not to say that they don't see magnetism at all, because if you now go and look at the inelastic spectrum, so so the x-axis here is momentum, y-axis is energy transfer. They do see signatures of inelastic scattering in the thing. So it's not that you're not seeing magnetism somehow, it's that the magnetism is not there in the ground state, but there is some magnetism in the excitations that you can visibly detect. So these are then the kind of puzzles that we were looking at, which is, how do you understand this entropy recovery being much less than what you expect? There is no sign of a second phase transition because the crystal stays basically also perfectly cubic down to below this transition temperature. And yet you want to understand, why there is no sign of magnetism, even though there is time reversal breaking and there is some spin gap in the system. Okay. So what I'll argue is in the next few slides, and I don't know how I'm doing for time here. Let me. Okay, I guess I'm already out of time. But maybe I'll give myself like 5 minutes to just go over the remaining few
Arun, don't
slides.
worry,
And
we had a lot of disruptions in the middle. So
yeah, so just feel free to stop me when you think it's all right. So the idea that we had was to actually imagine the following, which is, if, for instance, in an octahedral environment, right? So it's perfectly cubic, nothing has changed. Let's imagine that this j equal to 2 moment, which had 5 states, 5 levels, actually splits into a low energy doublet and a high energy triplet. Okay, and you can ask, well, why does this happen? It turns out that if you write down, and I can sort of, maybe, I don't know if I have a slide on this, but let me maybe scoot here and I'll go back to what I was saying. So it turns out that if you take into account the effective model for a j equal to 2, it turns out that in fact you can add additional terms, where in the crystal field problem, where in fact even maintaining perfect cubic symmetry, this thing will split into a doublet and a triplet. Okay. And so the idea then is that, you can work out what the wave functions of the doublet are and what the wave functions of this triplet are. Okay. And we find that the ground state here is basically what's called a non-Kramer's doublet. In other words, it's not a doublet protected by Kramer's theorem associated with time reversal symmetry, but rather it's a doublet where one state is made with Jz equal to 0, where the z direction, let's say, points along a crystal z direction. And the second state is made from a linear combination of Jz being 2 and minus 2. Okay. This triplet here, on the other hand, is made from the other state. So it's made from the 1, minus 1, and the combination where 2 and minus 2 come with a relative minus sign. That's what constitutes this triplet here. And so you see from here that, in fact, and one can show this carefully, is in fact, if you work out properly what the correct state of the system is, it's not a j equal to 2 magnet at all. In fact, the correct statement here is that the ground state is a non-Kramer's doublet of this sort, and the excited state is a magnetic triplet. Okay, and this gap, and one can sort of estimate this, is on the scale of 10 to 20 millivolts. Okay. So very quickly, this tells us that a lot of these results we can very quickly understand. The fact that there's a spin gap, you can see, because there is in fact no magnetism associated with the dipole moment between these states. Okay. So if I act with Jz, I get 0. If I act with J plus, I cannot connect to anything that lies within this doublet. J plus will connect any state here to one of these states up here. Okay. Similarly for J minus. So what you see is that the dipole operators that one likes to think about have no matrix elements at all in this low energy manifold. Okay. And so you expect that in fact there will be no dipole order in the system. The entropy, if this energy scale is large, is only the entropy that you see is the entropy of this non-Kramer's doublet. Okay. And finally, the spin gap in the neutron would be that you come in with a neutron, and the neutron dipole moment basically causes you to excite across this gap, because J plus would take you from this non-Kramer's doublet into a magnetic triplet. So it's something like an exciton which can disperse, but it's a gapped excitation in the system. Okay. So why does this happen? It turns out that this is kind of a little bit subtle. So the thing that one normally does, and one does this quite routinely in kind of, in the spirit of typical RG type spirit, would be to say, well, let me just throw away all the high energy scales in the problem, right? So you think about the T2G orbitals. I have 2 electrons. Think about the physics of this T2G. Right? And that's the starting point for most analysis of these kinds of systems. What we find here is, in fact, there is a perturbative effect where if we allow for, if we keep this EG orbital, in fact, that this 5-fold level that's here in this D2 system, there is a 5-fold ground state, and it turns out that ground state actually splits because of the fact that spin orbit can excite you into the EG and back. And so it turns out that there is a splitting of this order between the doublet and the triplet that I was showing earlier. Okay, so it's proportional to the Hund's coupling times the square of the spin orbit that excites you up and back, divided by this crystal field splitting, which is on the scale of 4 eV. So normally people say, well, V is large, let's forget about this. It's good for most things, but for questions of the sort that I was talking about, it's dangerous to just throw away the EG orbital. One has to kind of carefully keep track of it to see that these splittings actually emerge from a microscopic description. Okay. So once one does that, you can ask, well, what is the physics of this low energy doublet, right? So we've kind of understood that there is a low energy doublet in this J equal to 2 magnet. In fact, it's not J equal to 2, it's just a doublet that's important at low energy. And you can ask, well, physically, what do the Pauli operators that kind of take you between the two states of the doublet, what do they correspond to in terms of the microscopic angular momentum degrees of freedom? And it turns out that a pair of these, the tau x and tau z Pauli matrices, correspond to combinations which involve the square of the angular momentum. So there are things like jx square minus jy square or 3jz square minus j square. So these are time reversal invariant, okay? But they transform under lattice rotations and so on, but they're time reversal invariant. And these constitute an EG-like quadrupolar charge density, right? So you can associate these with basically some kind of charge orbital density in the system. Tau y, on the other hand, the third Pauli matrix here actually corresponds to a symmetrized product of 3 of these J matrices, right? So these are the J equal to 2 operators, by the way, okay? And then you take a symmetrized combination of Jx, Jy, and Jz. And now you see that this is an operator because it involves 3 J's. It breaks time reversal symmetry, but certain things like, for example, inversion, it's all even under inversion, and it has rotations, it has certain properties under rotations. But the point is that here is an operator that can actually break time reversal symmetry in the problem at low energy. Okay. So the guess then is that this is the operator that probably orders at the 50 Kelvin transition, because if these were to order, they would have broken lattice symmetries exactly like in the D1 system. So you would have seen some change in the lattice structure, which they don't in this particular example. They do not see any such thing. This one, on the other hand, preserves the cubic symmetry, but breaks time reversal symmetry. And so this can explain the muon spin rotation experiment. So what we've argued is that this is probably the one that's undergoing an ordering at this 50 Kelvin transition.
Arun, so this octopole can still couple with the Zeeman field linearly in the sense that obeying all the obeying all the lattice symmetries, or does it necessarily couple in a cubic fashion?
Not cubic, yeah, it's cubic.
Okay, so then is that seen in susceptibility experiments, the cubic dependence?
So in susceptibility experiments, I think it's hard to, so they don't see a simple linear behavior. But one of the difficulties, I think, is the fact that there are impurities in the system which they cannot get rid of. So how you do a subtract off the impurity response is a little tricky. But if you kind of apply a small enough field to somehow kill off what you think might be impurity physics, then it looks like you get something which is not simple linear response. The problem, I think, is that you have to kind of eliminate other sources of, right? So if you have like some kind of Van Vleck contribution, you have other contributions that you have to imagine subtracting off before you can do this. So if you do just the ordinary magnetic susceptibility in this case, the susceptibility as a function of temperature, it turns out that the susceptibility gets a contribution from the fact that there is this low energy triplet lying around. Yeah. So if you only zoom in on the doublet, you would argue that things should be like B cubed. But in fact, because of the fact that there is a thermal population of this triplet at any finite temperature, you'll have a small thermal population of this triplet. You get something where you can have some response that's a highly
even at a Kelvin temperature, 1 Kelvin or something.
Well, 1 Kelvin is where it's very hard because there is a large impurity response that they see at lower temperature in these systems, unfortunately.
Okay. And sorry for I didn't quite follow. Where did this number 20 MeV come from? Is it easy to understand why it is round about that ballpark?
You can sort of get it from here. Yeah. So the Hund's coupling is at about 200 millivolts. Sorry, did I get this wrong? I got this wrong. This should be a V square. Yeah. Sorry.
Yeah.
But so this, you can sort of plug in the numbers here, and basically extract out. So this is on the scale of like 10 to 20 millivolts.
Okay, thanks.
Yeah, just from this perturbation theory, you can sort of see that the number works out reasonably. Yeah.
Hi, Arun, Shubrata. Hi. I have a question about the algebra of these matrices. So I was just wondering, so the tau y matrix has a product of 3 of these J's, and tau x and tau z have products of 2 of these J's, right? So if I look at the commutator, then I would, I guess, get a product of, say, between ty and one of these, so tx and tz, I would get a product of 4 of these J's. But I guess a symmetric combination is going to pull out a factor of j squared and reduce it to a product of 2 of these J's, and so the commutation works out. I mean,
so the commutations work out once you project. You have to kind of make sure that you're not, so you can sort of work out within the doublet that you can sort of see that it works out. Yeah.
Okay, so right, so within the doublet, right, so you have to use the fact that j squared is a fixed number, and right, and that factor sort of comes out, and so the 4 J's that you have basically reduce to a number times 2 J's, I guess. And so
so if there are any single J's, for example, hanging around, then you would basically throw them away.
Okay, fine.
Because they would excite you into the triplet. Yeah.
Okay, thanks.
Yeah. Right. So the thing to ask, is to say, well, where is this interaction coming from that can stabilize tau y order? I mean, why should this magnetic octopole order? Because it already seems like a very complicated object containing jx, jy, jz. How can a simple, why not simple 2-spin interactions? Why don't you get something like ji dot jj? Sorry, j here being the angular momentum and this little j being the site index. But why don't things like this order in the system, right? And that has to do with the fact that even though you might think that magnetic interactions of this sort are the microscopically dominant things, or interactions of this sort that involve quadrupolar density interactions, you might think, oh, maybe there is some component of some Coulomb physics or something that gives rise to a quadrupolar interaction. You think all of these are actually important compared to something that's third order in the angular momentum at a site, which means if I want to write down an interaction that involves tau y, it will involve basically like 6 powers of j. And you would think this should be very subdominant. Okay, but in fact, that's not quite correct, because it turns out that, even though you can write down an operator like this, it can't do anything. Basically, if I look at a site j, the j operator at a site, the only thing it can do is excite you from the doublet into the triplet. And if the triplet is gapped, then basically this can't really do anything. Yeah. The same is true for these charge operators. So you can sort of take this rho xy, which is like the quadrupole operator, and act on it. And again, the only thing it can do is excite you, it turns out, into the triplet. So these operators, in fact, don't do anything directly. Okay. So you have to go to second order to treat microscopic operators of this sort. You would actually have to go to second order. And the way this arises is you basically excite through one of these J's, through some interaction like this Heisenberg interaction, you excite into a triplet. So both particles, for example, on the 2 sides, they will both excite into their corresponding triplets through this J. And then they can come back through this jx times jy product. So they go up through a dipole operator and they come back through this quadrupole operator. Now, and in fact, that's precisely how you get this kind of product at a site. So you kind of go through one dipole and you come back through a different quadrupole. Okay. And so you can work out that in this case, what you get is an effective, because it's second order perturbation theory, there is some ferromagnetic coupling here. So it's some negative sign here that couples tau y at site 1 and tau y at site 2. And so what you expect from here, from this microscopic picture, is that it's really these kind of perturbative effects of what you think are the dominant couplings. The perturbative effect gives rise to actually an octopolar, ferro-octupolar coupling in the system. And again, one can make crude estimates. We don't have, and I don't really have any very great microscopic this thing for what these numbers are, but you can use crude estimates and see that this is of the right order of magnitude. Yeah. And so with this, one can sort of explain some more details of the neutron scattering. You can sort of put this into a calculation where you look at not just the fact that there's this gapped magnetic triplet, which is a very local picture, but now once you include inter-site interactions, you get some dispersive magnetic exciton above this gap, around this gap scale. But more importantly, you can now kind of go and look at the effect of this octopole order. So it's some kind of time reversal breaking order, and you can estimate, the muon sits somewhere in the solid, around the oxygen site, and you can sort of see what the typical magnetic field is coming from this octopole order. And in fact, it turns out to be of the right order of magnitude, okay, within a factor of 2. So we estimated very crudely that it's about 30 Gauss. I think in the experiment it's like 50 or 60 Gauss. So, right. So this kind of seems like a reasonable picture. And one can sort of look at further experimental signatures, along the lines of what someone is asking. So if you want to actually look for this, one possibility is to kind of look at things like NMR. So imagine this is my osmium ion in the solid. This is the oxygen, and this is the other, whatever magnesium, some inert thing sitting here. And it turns out in the cubic system, you're basically along the oxygen basically sits on this line here that's connecting these two. Okay. And what that implies in this cubic system is that if I have octopolar order, it turns out that on this oxygen, if you do the magnetic field, satisfies the property that if I do a C4 rotation around this axis, then I interchange the minus and the plus. Okay, these go into each other. The magnetic fields will go into each other. And then if I do time reversal, I'm basically back to the old configuration. Okay, so the magnetic fields basically satisfy the property that if you do a C4 rotation followed by time reversal, you're back to where you started. And what this means is, in fact, that the net field, if you're sitting in the center here, the net field is going to be 0. Okay. Because that's an axis of which is C4 invariant kind of point there, then in fact, you would not see any magnetic field. And so oxygen NMR, for example, would not see this transition. In contrast to if it was dipole order, then you would have very clearly broken this, you would have seen some magnetic field at that site. Okay. But if you break the crystal symmetry, you will actually begin to see some NMR signature of these magnetic fields. So that would be one way to do, is to try and look at NMR. The other is to go back to what Rajdeep was asking, which is one can try and do Raman scattering. So this, unlike the quadripolar order I was showing earlier, this one we expect as purely ferro-octupolar. So it's a uniform order. But like what Shubhro said, it's not that you can couple to this very directly with magnetic fields. But it turns out that Jx, Jy, Jz, you can think of, imagine I think of it as a product of two operators, Jz times Jx, Jy. So it's really a product of a dipole times a quadrupole. Okay. So we know that if you apply a magnetic field, you can basically pin the dipole, right? And if you do that, then what the system does is it basically converts, in some sense, it takes what is an octopole order and converts it in some sense to a quadrupole order by condensing the dipole. Yeah, so you can think of this very crudely as saying that what if you do have quadrupole order, we know that there will be lattice distortion, right? And so one way to look at this is to do something like Raman measurements, where if you do Raman measurements in the, with or without a field, you expect to see that doublet to triplet transition as some peak here in the Raman signature. But if you apply a magnetic field, then in fact you expect that the crystal structure will transform from cubic to tetragonal when you put in a magnetic field. And so if you look at, and in that sense, I'm calling this B2G because that's for a tetragonal classification. Once you apply a magnetic field, in fact, you expect to see this change in the system as a quasi-elastic peak at low energy. Right. So in some sense, field-dependent Raman scattering measurements would be another way to track this octopolar order in the system. Yeah. So with that, let me conclude. Sorry, kind of went way over time here, but what we have argued is that that multipolar orders are kind of quite generic in systems with higher spins, and in fact we think that this might be kind of an example of octopolar order, which people have proposed in the context of heavy fermion, but I don't think that's been definitively shown in any of these systems. And so here is like a healthy 50 Kelvin transition, which hopefully one can try and do a lot of experiments in the future to try and nail down this physics here, which kind of seems to explain all the existing data. But all of these are, like in some sense, like it's like a negative data in the sense that you don't see crystal distortion, you don't see magnetic ordering, but it would be useful to have like a more positive signatures of this octopole order, possibly by using a couple of these experiments that I was showing you. Okay. So with that, let me thank my collaborators. So this kind of started thinking about some experiments from Bruce Dolan's group at McMaster University, and that's a student, Nalini, who did a lot of the X-ray diffraction neutron measurements that I was showing. This is my student Srikar, who kind of was involved in the later part, calculating some of the mu-SR signal and doing this perturbation theory that showing this doublet triplet splitting, from microscopics. And Graham Luke is the person who does mu-SR experiments, so we had kind of very useful discussions with him, and I've kind of put some references here if people want to look at it at some point. Right. So with that, I'll kind of leave this summary slide here, and if there are any further questions, we can discuss. Yeah.
Thank you, Arun. It was a very nice talk. So questions, we asked a few, but so I had one question, which is that because of the way you thought of this octopole as a dipole times a quadrupole, whether a pump probe type stuff where maybe you come up with a dipole, whatever optical stuff, and then you actually try to look at with maybe Raman or something, whether that kind of thing would work and would actually just give you the correct octopole order measurement. I mean, it might be very weak couplings, but
yeah, so I don't know. So it would be worth asking. So I don't know. So for example, you might think, well, if I excite, for example, a dipole excitation, if I make, then maybe I should start seeing some lattice vibrations or something, right? So the quadrupole might couple to the lattice. Maybe I start seeing some lattice. So these are actually interesting questions, which I mean, we've not really thought about them at all at this stage. But so one of the things I was kind of thinking, just as a fun thing, right? So one of the things people think about is, you have some twofold symmetry, right? It's either up or down, this Ising order. And so imagine I say, well, that's my memory, right? So imagine I say, well, I want to use my octopole as a way of storing information. Plus or minus one is some information. So then you might say, well, why bother doing it, right? And one of the arguments might be that, if it's something very hard for us to detect, probably the environment will also be hard to kind of couple. It's not really strictly true in this case, but at least, more complicated the order in some sense, the better it is. But on the other hand, I guess that's part of the reason for thinking about really for topological. This is not really a topological degree of freedom. But in that context, I was thinking of, how do you even change, right? Imagine you want to flip this from +1 to -1, right? Is there a suitable, pump probe? That's exactly, the kind of things that I've been thinking of, but I haven't really, had any useful thing there. But I don't know what, how do you change something from plus? You might do a spin flip. You might say, well, let's do some, like neutron scattering or something, right? Then you can flip something. But here it seems like a trickier
object to.
Yeah. So maybe one needs some multiple things, like you're saying, hit it with light and then do something else.
Yeah.
So there might be a clever way to, yeah.
So there's a question from a student, Shubhajit Sinha. Shubhajit, you can unmute and ask, actually.
Oh, okay. Thanks, sir, for the nice talk. So I was just wondering whether this LS coupling is mandatory for multipolar ordering. So I had some other pictures in mind. So let's say of systems that host like flat topological bands which are separated by small gaps that can mimic the degeneracy lifted to T2G levels of your picture and result in similar physics. So
Sorry,
was I clear?
Thinking of dispersing like flat bands with small dispersion and they mimic somehow the
T2G levels of your picture. Means I was just wondering whether some other system which can mimic your picture can also result in this kind of multipolar ordering, or LS coupling is mandatory?
No, it's not mandatory. So in fact, that's a good point. So for example, if one thinks about like the Kagome magnet, right? So for example, in the Kagome problem, or just electrons on the Kagome lattice, you would say, well, there is a flat band, right? And we certainly know that those states in the flat band you can more or less construct from thinking about local wave functions, right? So you can construct local wave functions made of, let's say, sites on a hexagon or something that will lead to these flat band states. If I think of, and not really Vanier, but some kind of local functions. But those, it's not clear to me that they have this kind of structure of local doublets. Maybe with spin you have something.
Okay, thanks.
Yeah, with spinless electrons, you probably have like one wave function per hexagon, for instance, on the Kagome when you construct the flat band states. But maybe in a more complicated lattice, I don't know if one can get like doublets out of these kinds of things with doublets. And then maybe one can talk about ordering within that flat band problem, right? So you can have, so that's a good point. Yeah. So I don't think it's necessary. It's just that it was, in this case, we were thinking about spin orbit physics, and these high spin degrees of freedom come very naturally in systems with spin orbit coupling. So that was part of the reason we were led to this. Yeah.
Okay. Any other questions?
Yeah, I'm pretty sure on the pyrochlore, I think one can get some of these states on the pyrochlore, maybe with like doublet kind of states constructed out of,
Okay, so let us thank Arun once for a very nice talk.
Thank you. Thanks.
Thank you, everybody.